This is an example problem of how to use Kirchhoff's current law in order to solve for a combination series and parallel circuit. So you'll notice in here, for this problem, I give you the total voltage, 10 volts, and I give you the three different resistors, R1, R2, and R3. Now the first thing I'm going to do here is I'm going to label my current. So I'm going to call the current power coming out of the power supply, this is the total. I'm going to call the current through R1, I1. I'm going to call the current through R2, I2, and the current through R3, I'm going to call that I sub 3. Now, if I look at my KCL, I have this node right here. I'll call that a node. And I have this other node over here. Those are the only two we really need to worry about. Don't need to worry about the one down here because it'll get covered by what we have up here at the top. So the first node is just that the total current equals I1. So the total current going into this spot is equal to the total current coming out. So that's important to understand that when we find I sub 1, that's the same as the total current. Then if we look at this node over here, it means that I1 going in is equal to the combination of I2 and I3 coming out of there. So basically the total current is equal to I2 and I3, which is fine. That'll help us later on down the road. Now the next thing I'm going to do is label the different voltages at some of the different spots. I know coming out of the power supply, since it's a 10 volt power supply, I have 10 volts at the very top because there's nothing in the way there. I know at the very bottom of the power supply I have 0 volts because I have nothing in the way there. So the potential here is just going to be 0 as well. Now, we are going to drop some of that potential across resistor R1. So I know that the 10 volts, it's going to go down. So the potential over here is going to be lower. I don't know exactly what that is. I'm just going to call that V sub x, since I'm not sure exactly what that's going to be. At the very bottom, I'm not dropping any potential at all. So I know that it's 0 volts all the way through. At the very bottom, at this point, would have lost all of its potential. So that's really important because we can use now our KCL equations along with Ohm's law to figure out how these voltages tie in. So for an example of that, I know that for resistor 1, that V1 equals I1 times R1. Now, because we're dealing with the currents here, I'm just going to divide both sides by R1. So I have I1 equals V1 over R1. So I'm just going to plug that in. So I know V1 over R1 is the same as current I1. I2 is just V2 over R2. I3 is, this should be a plus, V3 over R3. Now the next thing I'm going to do is substitute in what they mean and also some of the values since I know the resistors. Now what I mean by that is V1 I know is the voltage drop across this resistor, which means the voltage drop is how much it had before the resistor minus how much it has after. So we had 10 volts before, we have V sub x after. So 10 volts minus V sub x is the voltage drop across V1, or R1 I should say, that is V sub 1. That's divided by R1, which is 20 ohms. V2 is Vx minus 0, so it's just going to be Vx, that's divided by 33 ohms. V3 is just Vx minus 0, so that's just Vx, and that's divided by 51 ohms. Now if you look at this equation here, I have one variable, Vx. So I'm trying to solve for that Vx, and then I can use that to figure out V1, V2, and V3. So if I split up this fraction, I have 10 volts over 20 ohms minus Vx over 20 ohms equals Vx over 33 ohms plus Vx over 51 ohms. So I'm just going to add Vx over 20 ohms to both sides, just move all my Vx to one side. So I have 10 volts over 20 ohms equals Vx over 33 ohms plus Vx over 51 ohms plus Vx over 20 ohms. So basically I just have a fraction here. If I factor out the Vx, I'm left with 10 volts over 20 ohms equals Vx times, and then if I just combine these together, I'm going to get 13 over 132. I just did that on the calculator, just adding them up, and that's what I have. Now if I divide both sides by this 13 over 132, the ohms are going to cancel out, and we're left with just our voltage, Vx. So if I do that, I'm just going to round to 4 decimal places. I get 5.0769 volts. I would try not to round, because rounding is really important here. If you don't round, you're going to get a much better result. What we know, though, at this point, if I just keep this rounded, just so I don't write all of the decimal places in this example, is that the voltage at this spot is 5.0769 volts. So what that means is that I can fill in my different voltages, because I know across R2, it's just Vx. Across R3, it's just Vx. So V2 and V3 is just 5.0769 volts. So 5.0769 volts. For V1, it's not just that, but V1 is the difference. It's 10 volts minus this end result, and that tells us how much we dropped across R1. So 10 volts minus 5.0769 volts is 4.9231 volts. So there we go. Now the next thing I can do is I can figure out my currents. And figure out the currents, just Ohm's law. I know the voltages. I know the resistances. So V equals I times R. I can figure out that the current through I3 is 0.0995 amps. I can figure out that the current through I2 is 0.1538 amps. And then I1, I can just add those up to get I1. So if I just add 0.0995 plus 1.1538, I get 0.2533 amps. And if you remember from the beginning here, IT is equal to I1. So the total current is equal to I sub 1. So the total current is also 0.2533 amps. So if I just again use Ohm's law, I can figure out my total resistance here. So 10 divided by 0.2533 is equal to 39.4789 ohms. Now, just to show you something here, and this is kind of an important point, if I just use my equivalent resistance, and if I just use the resistors here and just try to find the equivalent resistance, I want to compare it, because that should be the same result if everything held up. So if I do 1 divided by R2, which is 33, plus 1 divided by 51, then 1 divided by that, after I add those up, I get 20.0357 ohms plus 20 ohms, because this is in series with those two. I should get an equivalent resistance of 40.0357 ohms. We're off a little bit, and it's not because we did anything wrong, it's because of the rounding. So you notice those values are off a pretty significant amount because we rounded to 4 decimal places. So even 4 decimal places, even though it seems like a lot, it really isn't that much for these circuit problems. So you really need to make sure that you just use the calculator and try not to round whenever possible.